Back in 2023, Apple's own researchers published a paper. It said your Mac could run an AI model twice as big as it has room for, by leaving most of it parked on the hard drive and only grabbing the bits it needs. Apple published it and then shipped nothing. 3 years later, somebody else built it, and they didn't stop at twice. A model that fills 15 gigabytes on disk now runs on a MacBook in about 2. So how is local AI on Apple Silicon suddenly using 7 times less memory? To figure out where the missing memory went, you have to look at what that original Apple machine learning research blueprint actually proved. The paper was called LLM in a Flash, and instead of loading an entire model into RAM at once, it proposed reading the weights directly from the drive on the fly. The system just leaves the bulk of the parameters sitting on flash storage, waits for the processor to ask for a specific piece of the model, and pages only that exact slice into active memory to compute the next token. They actually ran the numbers and proved they could run inference on models exactly twice the size of the available DRAM. So the theoretical math for running a model your machine literally has no room for is 3 years old, and it came straight from inside Apple. The math worked, the paper was public, and the hardware was already in your backpack. So why did it take 3 years and somebody entirely other than Apple for that exact blueprint to turn into something a person could actually run? Because if you just park a model on your drive and try to read the weights you need into memory for every single word it predicts, the physical drive simply can't push data to the processor fast enough. It technically works, but dragging gigabytes across the bus for every single token means you'd be waiting all afternoon for a basic script. So the actual hurdle back in 2023 was designing a system that could beat those naive loading approaches. And the math proved out, showing that by windowing the memory, they could speed up the graphics path by 20 to 25 times. Which means making the model readable fast enough to answer you was always the real challenge, since simply fitting it on the drive was just step 1. So who finally built the thing Apple described? And how far past Apple's number did they get? The answer to that is an open source project called Turbo Fieldfare, which was written specifically for Apple's own chips and graphics layer to do exactly what that original research promised. And according to the write-up covering its release, they're running a 26 billion parameter model on a standard MacBook using only about 2 gigabytes of active memory, because the rest of the model never actually enters RAM and just stays parked on the drive. So the claim is real, and it's documented, giving you a model that's technically way too big for your hardware, just running locally like it belongs there. But if you run the numbers on that, we've got a pretty serious arithmetic problem. Apple's 2023 paper promised to run models twice the size of your available memory, but this new result delivers roughly a 7 times reduction. So where exactly did all that extra saving come from? When you run inference, the system figures out exactly which slice of the model it needs to predict the very next word, pulls only those specific weights into memory, runs the math, and then immediately fires them into the sun. Because it drops the data right after using it, your memory just holds a tight, moving window of the model as it generates text, essentially treating your RAM like a revolving door instead of a parking lot. On its own, this windowing trick is exactly what Apple proved, and it perfectly accounts for how you're able to run an AI twice the size of the available DRAM. The mechanism is real, and it gets you a steep hardware discount. But a 2 times reduction is obviously a very long way from a 7 times reduction. And that leaves you looking at that missing 5 times multiplier and wondering if a leap this big actually holds up on a normal consumer laptop you'd actually buy, or if it only survives on the specific test rig it was built on. So where did the rest of the memory saving come from? It arrived because the open models themselves changed shape after 2023. If you pull up a technical breakdown for a newer release like Gemma 4, you'll see it relies on an architecture called Mixture of Experts, which is really just an academic way of saying the neural network is no longer one solid block of math. Instead, the model is split into a set of small specialist sections, and a router looks at your prompt to pick only a handful of those sections for each word. According to the project's write-up, the model only activates 8 of those sections at a time, meaning roughly 85% of the network is asleep at any given moment. And it turns out that an ELDA section of code is exactly what you can afford to leave parked on a solid-state drive. So the missing multiple belongs entirely to the model's learning how to sleep on the job, which is what made Apple's old loading trick worth building. If the model is doing most of the work, why does this only run properly on a Mac? Because a normal PC treats its main processor and its graphics card like two divorced parents who refuse to speak directly to each other. If you run AI on a standard rig, you use the GPU, which means every time the processor pulls a sleeping model section off the drive, it has to physically copy that data into the graphics card's separate memory pool. That copy step is a toll booth, and if you're rapidly pulling hundreds of tiny fragments into memory every second, the traffic instantly backs up and the system chokes. But Apple's silicon is built around a unified memory design, meaning the processor and the graphics cores share the exact same pool of RAM. There's no copy step, so the second Turbo Fieldfare yanks a fragment off the drive, the graphics cores can read it right where it sits. That zero-copy handoff is what makes the juggling survivable, which means this whole approach is a distinctly hardware-shaped trick that relies on the architecture inside something like an M4 Max. So we know the model finally fits, but is it actually fast enough to be worth using? Or is this just an academic party trick? The published cross-generation measurements on Apple Silicon, using a standard runner like llama.cpp, prove this is not some fragile demo that only survives a screenshot. Instead of vendor claims, these are real benchmarks taken in mid-2026 using standard 4-bit Q4 KM quantization, and they put everyday laptops in usable territory rather than novelty territory. A higher-end chip like an M2 Max is going to chew through your prompts faster than the dented base model Air you bought for college. But the gap between them is just a matter of degree now, rather than a strict line between possible and impossible. If you fire this up in the terminal today and watch the output stream in, you are getting usable working speeds on ordinary machines. So the giant model fits, the windowing trick works, and the hardware delivers the answers fast enough to keep your attention from wandering. But violently yanking idle experts off your local storage drive for every single word you generate has to draw blood from somewhere. That leaves the glaring question of what exactly your machine is spending to save all that memory. What it's spending is your drive's read speed, which suddenly goes from being a static spec you check once when you buy the laptop to a live performance component dictating exactly how fast the AI can answer you. Since the machine has to keep running those fresh reads constantly for as long as the model is talking, your storage drive is no longer just a digital filing cabinet, which means it's now the active engine driving the inference loop. So the bottleneck didn't actually disappear, it just got relocated. Memory stopped being the limiting factor, and the drive just inherited the problem, shifting the entire weight of the system onto a component nobody pays attention to unless they refuse to pay for iCloud. And that's a brilliant trade to make if you assume all laptop storage performs roughly the same. But that leaves the glaring question of how much two drives can actually differ from each other. The answer is that two seemingly identical machines pulled from the same shelf might not actually be identical inside, because certain units at one specific storage tier shipped with different hardware. If you look at this report from Tom's Hardware, you'll find that some units of the MacBook Air M3 actually shipped with an extra NAND chip crammed onto the logic board. And as the report explains, having two chips instead of one allows the system to read from both of them in parallel, which makes the laptop drastically faster than identical predecessors sitting at the exact same nominal capacity. So with your performance now bound to storage speed, you are basically at the mercy of an extra NAND chip that you either won or lost on the assembly line. Which means the one component this whole trick leans on is not a fixed quantity, even between two laptops sold as the exact same product. But the drive is only one variable, which leaves the question of what else changes between two of the same machine. Okay, so the storage lottery explains part of the gap between two identical laptops, but it doesn't explain what happens when you leave the benchmark page and actually use them for an hour. The headline speeds you see published everywhere are snapshots, usually taken over a few seconds of burst generation. But the entry-level laptops most people actually buy to run this stuff have absolutely no fan inside them, which means the only way they survive sustained load without melting into your desk is by artificially slowing the chip down. And from what people are reporting, doing constant local AI work triggers exactly that kind of thermal throttling. Which means a short test and a long session are two completely different measurements, and the machine you most likely want to run this on is the one least capable of holding that snapshot speed for an hour. So is there a single spec you can actually check to predict any of this before you hand over your money? The good news is that these speeds hold up on a laptop a normal person might actually buy, provided you know exactly which line on the spec sheet to look at. Because the whole trick relies on constantly shuttling data around rather than just parking it, the strongest predictor of local AI performance isn't your graphics core count or some dedicated neural hardware. According to benchmark comparisons published in early 2026, the one number that actually dictates how fast a machine can answer you is memory bandwidth. That figure is printed directly on the product pages, and it spans roughly an order of magnitude, scaling up massively from the early base models all the way to top-tier chips like the M5 Max. It's the single most important metric for this entire workflow, and it is almost always the exact line buyers skip right past on their way to checking the memory capacity. But even if you buy the absolute highest bandwidth machine on the market, you still have to figure out if this drive loading trick actually works for the specific model you want to run, or if it only functions on a handful of specially shaped architectures. Because if you take this exact same hardware and point it at a solid, non-sectioned model like Qwen 3.627B, the entire illusion immediately collapses. Even when you compress it down to 4-bit settings at the Q4KM tier, it still needs something in the region of 17 gigabytes to run. And if you try to run it at its full BF16 precision, that number balloons to roughly 56 gigabytes of space you simply don't have. In a dense architecture like that, every single piece of the neural network fires for every single word generated, which means absolutely nothing is ever idle, and there is nothing you can safely leave parked on the drive. So the memory saving is strictly a physical property of how the model was constructed, which means you can't just switch it on for whatever repo you downloaded today and expect the machine to magically invent the missing space. Point this trick at a standard solid model, and the old memory requirement comes straight back. So after all that, what is the 7 times actually measuring? So when they quote that 7 times figure, it is specifically measured against the baseline of loading that entire squashed Q4KM model into your RAM all at once, like some kind of digital hoarder. And if you change the math and measure it against running the model at full BF16 precision instead, the gap gets so laughably wide that marketing teams can start quoting absolute nonsense memory savings without technically committing fraud. But whichever convenient multiple you choose to believe, the physical footprint on your machine never moves. The file sitting on your SSD is exactly the same size it always was, because your drive still has to warehouse every single one of those idle sections, even when your active memory gets to ignore them. So if the model's architecture is doing the overwhelming majority of the saving here, what did Apple actually contribute to this equation? And what happens to this entire trick when the next generation of models decides to change shape again? So the reason it took 3 years for anyone to actually build the thing Apple wrote that LLM in a flash paper about is that back in 2023, models were still solid blocks of math where every piece had to be active at once. The researchers proved you could run a model twice the size of the available DRAM by cycling data off the drive, which is a neat trick, but a doubling is still a long way from a 7-fold drop. That missing multiple only showed up when the models themselves changed shape, splitting into a mixture of experts where, as the write-ups covering the demo point out, the architecture deliberately leaves most of the network asleep for any given word. Apple's hardware trick was just sitting there waiting, and the open source model architecture finally caught up to make leaving things on the drive actually worth doing. which means this efficiency gain is really just two completely independent timelines crashing into each other. The memory saving belongs entirely to how the model was constructed, so that travels with whatever you download, while the speed it runs at relies on Apple's unified memory, which is the part you still have to buy. And if the next frontier model goes back to being a solid brick of math where nothing sleeps, you're going right back to paying Apple for the privilege of holding it all in memory. Anyways, that's all folks.